Okay, this is following up on our previous discussions of atomic theory, and we're looking at the last of three discussions on what is going on with the electrons in a molecule. So last we were talking about the different sublevels that are within an atom, the S, the P, the D, and the F, and we discussed their various shapes and how many electrons can fit together. And then we put those on a periodic table to see how it all fits together. Now I've made some changes to your notes here in section 11.8, the wave mechanical model. And so you might need to write some things in that aren't on your current set of notes. So as we said before, a given orbital can only hold a maximum of 2 electrons, and those 2 electrons will have opposite spin. So the 2 electrons have opposite spin. This was discovered by a gentleman last name Pauli, and it's called the Pauli exclusion principle. And this has to do with the magnetism that's created by a moving electron. And so we designate the spin of these with arrows, and we use just an up arrow and a down arrow. One arrow represents an electron spinning in the clockwise fashion, and we usually put that one first. And the other arrow pointing down is going to be spinning in the counterclockwise direction. So as we go to this next page, you'll see how we use this in what we call orbital diagrams. In addition to that, it's important for you to know the Aufbau principle, and don't worry about memorizing these names, just know how to use them in drawing electron configurations and orbital diagrams. An electron will go into the lowest energy position available. So if it has a choice between 1s or the higher energy level 2s, if 1s is open and available, it's going to go there. If there's only one electron in 1s, there's room for another, it would rather spin in the opposite direction than do the jump up to the next energy level. That takes too much work, and electrons try to exert the lowest amount of energy possible. So the last rule, this is called Hund's rule, sometimes called the seats on a bus rule, says that if electrons are going to go into equivalent orbitals, then see the 3 orbitals of the p, those electrons are going to go into the next orbital spinning in the same direction rather than pair up. So this is how it should be done if there were 4 electrons going into a p orbital. If there are 2 electrons going into a d orbital, then what you will see is a picture like this. Let me show you what will never be true, unless it's an excited atom, is that the p electrons drawn on the left should never look like this. There should not be an empty orbital within the p sublevel if there are paired electrons. And likewise, in D, they would not want to go into the same seat on the bus if they have individual seats available. So just to emphasize, I want to cross this out and say that is not going to happen. Your pictures would look more like these here on the left, following those rules. Okay, so we're going to do the electron arrangement for the first 18 atoms, and I walk through the first few, and then I will go offline and show the completed orbital diagrams, pointing out some notable exceptions as you go through. So let's begin with hydrogen. Hydrogen has 1 electron. I looked on the periodic table and I saw that. It's going to go into the first available energy level, that's the 1s, and it will have a configuration of 1s, and then you superscript a 1, as in 1 electron. Helium has 2 electrons, and they're going to go into the 1s, but the second electron must spin in the opposite direction, and then the electron configuration is going to read 1s2. We don't say 1s squared. So these first 2 electrons, for what helium only has 2, they are going to go to the first energy level because it's the lowest energy level possible. And so they pair up in that level rather than go to the 2s. Lithium has 3 electrons. The first 2 go into the 1s just like above, and then there's 1 that's available to go in, but it chooses to go into the 2s because that's the lowest possible energy level available, and it's going to spin in the up direction. So the way we write that is there are 2 electrons in the 1s, so 1s2, and then there is 1 electron in the 2s. And that pattern is going to repeat. So allow me to pause. So as you see, I have filled in the beryllium, and I get tired of doing arrows, so I do little half arrows. And beryllium's electron configuration is 1s2, 2s2. And by the way, I did forget to say that these pictures are called orbital diagrams. That is how they are referred, and they tell us about the spin of electrons. If we look at electron configuration, it does not tell us how the electrons are arranging themselves. And how the electron spins has to do with magnetism. So for boron, we have 1s2, 2s2, and then the next electron goes into the 2p, and there's only 1 there. So when we get to carbon, which has 6, we're now going to have to apply the Pauli exclusion principle that says these electrons are going to they're going to pair up only 2 maximum. The lowest energy levels available for them are the 1s, the 2s, and the 2p. That's the Aufbau principle. And then finally, Hund's rule says that as long as there are equal orbitals available, the electrons are going to go into individual places. So for carbon, we have 1s2, 2s2, 2p2. And then nitrogen will do the following: up, up, and up. They will all 3 go up before they pair up. So when we get to oxygen, you will get 8 electrons, and I'm getting the numbers of electrons because all of these are in the are on the periodic table. I'm just doing them right in order. 1 electron, 2, 3, 4, 5, 6, 7, and 8. And now I'm going to go offline, and I will complete a good portion of the rest of the table here. Now that I've reached neon, I want you to notice a couple of things. There's a little asterisk by it, and what that means is that's a noble gas. A noble gas is special for a couple of reasons. First of all, if you look at how this diagram is built, you will see that we have completed, and I'm having a little page issue here. Let me try to fix that. So you'll see that neon has completed the first energy level and the second energy level. This box represents the third energy level, and neon has filled up everything up until the third energy level. That is what a noble gas is. For some reason, filling an energy level is a very stable place to be, and that's why neon doesn't react with anything. Notice the same is true with helium. Helium has 2 electrons. They're both in the first energy level. That's a complete energy level. So we are now at the point where there is no unpaired electrons, and helium is also a non-reactive entity. So what we're seeing is that when that S and P are full, we have a complete energy level. So when we're doing electron configurations, this doesn't change our orbital diagrams at all, but it does change what we do when we get to the orbital electron configuration. We use what's called a noble gas abbreviation. We can put neon in brackets, and neon represents 1s2, 2s2, 2p6, so that fills everything, and then there is just one electron in the 3s1, and that would complete the electron configuration for that element. I'm going to fill the rest of these in, and you can check your work when I come back in just a moment. There is your completed orbital diagram. If you'd like to pause and check your work, you should do so. You will notice that there is a steady progression, and we're putting unpaired electrons into the 3p until we're forced at sulfur to pair them up. And you'll notice that I used the noble gas abbreviation for all of my electron configurations. Note once again, argon with 18 electrons is a noble gas, and we have filled up the S electrons in the third energy level and the P electrons in the third energy level. This is a very stable place to be, a beautiful place for the atom. It's a desired position, and we'll see how that influences further developments. So we're going to talk about valence electrons, and valence electrons are the outermost electrons, and they are very important in chemistry because they are available for chemical reactions. So chemistry is all about the electrons interacting between atoms, and the valence electrons are the outermost electrons that actually help chemical reactions to proceed. And there are some things that you know already that I want to just show you on the periodic table how that plays out. We've talked before about everything in this column having a +1 charge, everything here +2. Jump across the transition metals and we have +3. We're not going to worry about this column. And then we have -3, -2, -1, and there's no charge. Noble gases have no charge because they don't gain or lose electrons. They don't want to interact with others. You get to be +1 by losing an electron. So sodium or lithium and sodium all want to have a +1 charge. So let's go back to their electron configurations and see why that might be true. So lithium is right here. It has an electron in the 1s orbital, and that 1s orbital, that lone electron here, is not held onto as tightly as the core electrons. So this is called the valence electron, and the filled energy below it, filled energy level below it, those are called core electrons. So this one valence electron is the electron that is lost when lithium becomes a +1 ion. Let's look at sodium. So the lithium is in the 2s1. Where is sodium's last electron? Sodium's last electron is in 1s1, or I'm sorry, 3s1. So that's the electron that sodium loses. As long as we're here in this chart, let's look at the next column, which would be beryllium. Here's beryllium. When it reacts, it gets a +2 charge, and it does that by losing these 2 valence electrons. After sodium comes magnesium. Magnesium has 2 electrons in the 3s2 position. It loses those 2 valence electrons and becomes magnesium with a +2 charge. So what we're seeing is these electron configurations are telling us that all of these atoms in this column are going to lose 1 electron, and that electron is going to be in the 1s, 1 position. This column, which is beryllium, magnesium, etc., are going to lose 2 electrons. They lose both of their s electrons. This column is going to lose 2 electrons from S and 1 from the P level. So that would be aluminum. See, aluminum has three valence electrons. And is there anything like that up above? There is boron, which has 3 valence electrons. So we call these valence electrons the electrons that are available to interact and cause or help chemical reactions to occur. When we talk about the nonmetals, what they're doing is they are gaining electrons. And I misspelled gaining, I'm sorry. They are gaining electrons in order to become negatively charged ions. So chlorine is going to gain 1 electron, as well as fluorine. So fluorine, chlorine, bromine, and iodine are going to be very similar. And let's take a look at what those similarities entail. They all have electrons that fill up the P, but they're missing 1 electron. If they gain that 1 electron, they would be stable like a noble gas. So they're looking to gain an electron. And then before chlorine comes fluorine. And once again, it's 1 electron short of being just like a noble gas's electron configuration. And for some reason, that filled s and p orbital is a very good place to be. So we're going to see how this plays out. When I was a student, there were a variety of ways that we learned how to determine the order in which electrons went in. I would not recommend this method, although some people do enjoy it. We're going to use the periodic table to identify how the electrons fill. So up above, you'll see that we followed an order of 1s, and then 2s, and then we did 2p, and then 3s. And after 3s, we did 3p, and then 4s. Oh, wait, 4s gets filled before 3d? Yes, that is true. So then, after we fill 4s, we go to 3d, then go to 4p, and then to 5s. So this little diagonal diagram, which you could follow by making your own little sequence of the orbitals, and then drawing diagonal lines to determine how they fill up, could be one method of knowing how to fill orbitals. Or what I would recommend is using the periodic table to identify how you fill the orbitals. We started out previously with an upside down triangle. We cut that in half twice, and then we drew parallel lines, and we filled in each energy level that contains the electrons. So the first energy level, the second, the third, and the fourth. And we say there are 1s, 2s, and 2p electrons. These are sublevels within an energy level. We have 3s, 3p, 3d, 4s, 4p, 4d, and 4f. And we're going to note that this is the first period on the periodic table. Below it you'll find the second period. I'm sorry, I'm having a little difficulty here. And below that, my goodness, the third and the fourth, etc. So the way that we're going to complete or discover how we do the orbitals in order so that we follow a good, clear methodology is that we're going to fill in everything one energy level at a time. So we start with the 1s, and the 1s will be followed with the 2s underneath it, 3s, so 4s, 5s, 6s, 7s. And then we note that in the second energy level, we have the first opportunity to have p block electrons. And so the p block electrons begin at 2p, and you'll note that they're in the second energy level. 3p, 4p, 5p, and 6p. And these go over these 6. So there are 3 orbitals within the p level. Each of them holds 2 electrons, so there are 6 blocks across that make up the p block of electrons. For s, you've got the 2 electrons, and then we have d. And here we're coming to a little bit of a surprise in that the first energy level that allows d electrons is the third energy level. So this is going to get labeled 3d, but note that it's in the fourth period energy level. And that's not what we would expect, but there is evidence that suggests that this is how it works, and so that's what we're going to go with for atomic theory. So we just fill in 3d, 4d, 5d, and 6d. And for our class, we're not going to be discussing the lanthanides and actinides, but the fourth energy level is the first energy level, which allows f electrons. So we label the lanthanides 4f and the actinides as 5f. And just so that you recall, this is the order that they would fill. They would fill 4f before completing 5d. And if you go from 7s, you're going to go 7s to 5f to 6d to 7p before you would continue on your way. And that would complete our filling in of the periodic table. Why does atomic theory seem right? Well, there's a couple of reasons I'd like to put out there. First of all, Mendeleev created the periodic table based upon chemical and physical properties of elements. And that was matched by de Broglie and Schrodinger's atomic theory. It fits the look of the periodic table. So which came first? Was it Mendeleev or de Broglie and Schrodinger? Schrodinger, sorry about that. De Broglie and Schrodinger came well after Mendeleev, and de Broglie and Schrodinger came up with the theory that we currently use, but the periodic table, the physical evidence, is first. The mathematical model, which is the theory, matches the periodic table. There's 2 basic classifications on the periodic table. we have metals and nonmetals, and they are separated by what are called metalloids, things that have properties similar sometimes to the metals and other times they're similar to the nonmetals. But we want to talk about these great big categories, and within a family of metals, metals tend to lose electrons. Okay? So the one that is more likely to give up electron is a metal that is near the bottom. And for that reason, metals that are at the lower part of the periodic table tend to be more reactive because they love to give away their electrons. If an electron is farther from the nucleus in a higher energy level, that means it's going to be lost more easily. Nonmetals, they want to gain electrons. Therefore, the smaller of an atom, the more reactive a nonmetal is going to be. So the smaller nonmetals, excluding of course the noble gases because they don't react with anything, is going to be the most reactive of the nonmetals. So if we could draw a little line in here, we would see that the split between the metals and the nonmetals is going to look something like that. You have your metalloids going through this part of the periodic table. So the smallest nonmetal is going to be fluorine, which tends to be the most reactive. And the most reactive metal is going to be cesium because its electrons are farthest away. So we're going to talk about a couple of trends here in addition to what I just mentioned. And those trends are going to be the atomic radius. So as you go from left to right on the periodic table, the size of the atoms is getting smaller. This reflects what we learned about Coulomb's law, that there is a greater charge in the nucleus attracting electrons basically at the same distance from the nucleus, leading to a decreasing size as we go from left to right across a period in the periodic table. But as we go down a column, the electrons are actually going into higher energy levels farther from the nucleus. So Coulomb's law says they all have the same basic attractive force, but the distance is increasing, therefore making the atoms larger. So the trends are in atomic size decreases from left to right, and atomic size increases from top to bottom. And these arrows are going to indicate those trends for you. Why does it increase as you go down? Because electrons are added at higher energy levels, and those higher energy levels are farther from the nucleus, farther from that positive charge which attracts them. And then, why does it decrease as you go down, or why does it decrease as you go from left to right? Increasing numbers of protons, and I'll use the hashtag for numbers, increasing numbers of protons, that's P+, attract the electrons at the same distance. And this is all from Coulomb's law that we can learn this. So the last trend that we want to talk about is ionization energy. And ionization energy is the ability to remove the outermost electron from an atom. So the one that would be farthest away. And the trend is the larger the atom, the easier it is to remove, because that last electron is farther away. Therefore, it's easiest. So if I look at this group right here, cesium, barium, tellurium, lead, bismuth, polonium, astatine, and radon, the ionization energy, and I'll just abbreviate that IE, is lowest. The energy required to remove an electron from cesium is lower than it is for radon. Ionization energy is high, and that's due to the fact that radon is holding its electrons very, very closely to itself, whereas cesium has its electrons fairly far away. So the attractive force in the nucleus is greater for radon than it is for cesium. Radon is holding on tightly, therefore it takes more energy to remove that electron. Cesium is holding on loosely, and it takes very little energy to remove its electrons. So these are the trends that you'll want to know. They will influence the atom's behavior as we move into talking about chemical reactions. This is the end of our talk.